Hello, I'm Noor and I'm presenting our work from Qualcomm AI Research. Compared to handcrafted codecs, neural video codecs have achieved competitive rate distortion performance. However, when we consider their practical deployment, there are a few challenges. Rate distortion optimization leads to reconstructions that may not correlate with human visual system. For example, in this image, typical codecs may code the foreground and background regions in a similar manner. However, a user might focus on the foreground texture in the frame rather than the background field. Another challenge is that typically neural codecs are trained for a particular bitrate. Operating at multiple bitrates would mean storage overhead. Since neural codecs appear as a black box during inference, users may have very little control over reconstruction quality. Our design addresses these issues by building a variable rate and a variable distortion codec. We begin by considering a flexible rate codec that navigates the rate distortion plane using a single model. To integrate semantic information, our codec accepts ROI masks that specify foreground and background regions. It can also work without them. Such a setup allows for flexible distortion coding, which gives better ROI RD performance if needed. We operate a neural codec in low delay mode. We base our architecture on scale space flow model. Our iframe codec is a regular hyperprior autoencoder. Our p-frame codec predicts an approximate version of current frame from previous frame using optical flow estimation and residual prediction. We add multi-rate capability via beta conditioning and multi-distortion through ROI mask conditioning. We modify training objective as follows. Here we show an iframe codec with input frames X encoded to produce latent Z0. The decoder generates reconstruction X hat. Our codec is conditioned on rate tradeoff parameter beta that is also used in the training objective. We extend this objective to also reflect semantic aware coding. The encoder now accepts semantic masks as input. Distortion loss now reflects the trade-off in ROI versus non-ROI region using parameter alpha. This parameter can be sampled during training and can be varied at test time. For training our models as well as baselines, we use Vimeo 90K dataset. During training, we generate temporally consistent ROI masks using Perlin noise. These have no semantic connection to training data. Here we present results on Davis validation subset. We also evaluate on compression benchmark datasets. These results can be found in our paper. Our quantitative results include bitrate versus PSNR plots. At alpha 1, we match baseline performance. Here we treat the entire frame as foreground. At higher alphas, we gain up to 5 dB in ROI PSNR with a 2 to 3 dB drop in non-ROI regions, which we found to be visually not harmful. We also plot PD-rate performance of ROI versus non-ROI region using a single distortion model as a baseline. We see that as we increase alpha, indicated by increased size of the blue markers, we get huge PD-rate gains in ROI region. We further confirm our results visually. Compared to the baseline SSF model, we gain better performance in ROI with a slightly blurrier background. We also observe that for smaller alpha, we save up to 25% in bitrate without significant loss in background perceptual quality. Thank you for listening.